Currently teaching in Chicago and the Hebrew University. Previously a postdoc at Weizmann and PhD at the Hebrew University.
Thank you very much. It's a pleasure to be here. So, as you all know, neural networks have made a major technological revolution and they have many useful applications. But in spite of this impressive practical success of neural networks, our theoretical understanding of how deep learning works is still quite limited. And one might ask, why should we care about deep learning theory? If it works so well in practice, why do we need a better theoretical understanding of how it works? And I think that perhaps the most important reason is that if we don't understand the technology, then it is more difficult to improve it. And so if we hope to keep improving in the long term and to overcome current limitations of deep learning, it might be helpful to have better theoretical insights. And also, theoretical understanding might be useful for preventing malicious attacks and overcoming some privacy issues and safety issues and other issues that we have today in AI systems. Now, I will start this talk by providing some basic preliminaries on supervised learning and specifically on learning using neural networks. So the first few minutes of this talk are a basic introduction, and then I will get to the main topic of the talk. In supervised learning, we have some unknown distribution D over examples. In this talk, each example xy would usually be such that x is a vector in Rd, and y is the label, which will be in the set -1 plus 1. This setting where the labels are either -1 or +1 is called binary classification. So we will mostly focus on binary classification. And the main task to consider is given some data sets drawn independently from the distribution D. We want to return some function h, also called hypothesis or predictor, such that if we choose a test example, if we choose a fresh example from the distribution D, then its probability should be labeled correctly. Okay, so if we choose xy from D, then the probability that h of x is not equal to y should be small. And in this talk, we want to learn using neural networks. So the function h that we want to return is a neural network. And specifically, we will focus on fully connected random neural networks. And let's briefly recall what it means. So each neuron in the network computes a function of this form, where x is the input to the neuron, w is the weight vector of the neuron, and b is the bias term. And sigma is the activation function. And in this talk, we will mostly talk about the radio activation, which is shown here in this figure. And we'll mostly focus on fully connected networks, which means that each neuron is connected to all neurons from the previous layer. And we define the depth of the network as the number of layers. For example, this network is depth 3, and the width is the maximal number of neurons in a layer. For example, the width here is 4. Now, let's denote the network by phi of theta and x, where theta are the parameters, namely the collection of all weight vectors and bias terms of all the neurons, and x is the input to the network. Now we can restate our law as follows. We're given some training data sets drawn from the distribution D, and we want to find some parameters that such that if we choose a random test example, if we choose a fresh example from D, then it should be labeled correctly with high probability. So if we choose xy from D, then the sign of the output should correspond to y with high probability. Okay, now, of course, the question is how can we find such a good network? And the common way to do it is by trying to minimize an objective, which is called the training loss. The training loss is given here. And essentially, this training loss gives a small value, a small output, if the network performs well on the training examples. So by minimizing this training loss, we're essentially looking for a network that performs well on the training examples. And the function L inside the sum here is called the loss function. In this talk, we'll focus on the logistic loss function, which is shown here. It's also called binary cross entropy, and it is a very common loss function for binary classification. And then the question is, how can we minimize the training loss? And the common way to minimize the training loss is by using some variant of the gradient descent algorithm. So in order to minimize this training loss, we start with some random parameter of theta. And then in each iteration of gradient descent, we make a step in the direction opposite to the gradient of the training loss until hopefully we reach some minimum. And in addition to gradient descent, we'll also discuss in this talk gradient slope, which corresponds to gradient descent with an infinitesimally small step size. So here, in addition to the discrete trajectory with gradient descent, we also see the continuous trajectory with gradient flow, which corresponds to having very small steps in the gradient descent. Now, when we recall that our goal is to find a network that performs well on test examples, on stretch examples from the distribution D. But when we minimize the training loss, we are essentially looking for a network that performs well on the training data. Now, if gradient descent finds a network that performs well on training data and also performs well on test data, we will say that this network generalizes well. However, if it performs well on the training data but does not perform well on test data, we will say that we have overfitting or harmful overfitting. Okay, and the last basic notion that I want to discuss in this introduction is adversarial examples. So an adversarial example or adversarial perturbation for a given input and a given trained model is a small perturbation, such that if we add this perturbation to the input, we get another input which is very close to the original one. It looks similar, but it's classified differently by the network. For example, here we might have an image of the duck, and then after adding a small perturbation, you get an image which still looks like the original one, but now it is classified by the network as a horse. Now, these kind of adversarial examples are known to be very common in practice. Trained neural networks tend to be non-robust to adversarial examples. But from the theoretical point of view, it is not sufficiently clear why trained neural networks are so vulnerable to adversarial examples. Okay. Now, my research in general considers deep learning theory, and more specifically, most of my works in recent years belong to one of these four topics, which are mentioned here. The first two topics are implicit bias and benign overfitting, and these are the subject of this talk, and I will elaborate more about these topics in the rest of this talk. And specifically, I will touch upon this subset of papers which are highlighted here. And in addition to these two topics, I also study computational complexity of learning neural networks, where the main question is, given examples labeled by an unknown neural network, can we find in polynomial time a hypothesis with good test performance? Namely, we want to understand in what situations we can learn neural networks in polynomial time, and in what situations we can prove hardness of learning of neural networks under the standard assumptions. And the main motivation is to understand what assumptions on the setting might suffice to allow for efficient learning. And the first topic here is the benefits of depth for expressivity, where the main question is how does the network's depth affect its expressive power, or what are the trade-offs between the depth and the width of the network in terms of the expressiveness of the network. Okay, so in this talk we'll have two parts. In the first part we'll discuss the notion of implicit bias, and in the second part, which will be a bit shorter, we'll discuss a phenomenon called benign overfitting. So let's start by discussing implicit bias and its implications. Neural networks are often over-parameterized, which means that the number of parameters in the network might be larger than the number of training examples. And in such situations, there are typically many different solutions, many different neural networks that perfectly fit the training data. But from this large set of possible solutions, some of these networks also generalize well on test examples, but other solutions only overfit the training data but do not generalize well. But still, empirically, it seems that gradient methods often converge to the good solutions, to the solutions that also generalize well. So it seems that in many situations, the training algorithm is biased towards certain solutions which generalize well. And this so-called implicit bias has been a subject of extensive research in recent years, and it is believed that understanding this implicit bias might be a key for understanding generalization in deep learning, which is a very fundamental question. Now, in order to discuss the implicit bias and its implications, we need to first try to characterize the implicit bias. So we want to understand what are the properties of solutions that gradient descent prefers. So from the large set of possible networks that perfectly fit the training data, we want to understand what are the properties of the networks that gradient descent will actually converge to. And we can start by thinking about the simpler case of linear predictors. So suppose that we have this data set with some positive examples and some negative examples. And this data set is linearly separate. So we can perfectly fit it with a linear predictor. And in fact, we can fit it with infinitely many possible linear predictors For example, here we see 3 examples for such linear predictors. And then the question is, from this large set of possible solutions, to which solution will gradient descent converge? And the answer for this question was shown by Vardi et al. They showed that for a linear predictor trained on linearly separable dataset, gradient descent converges in direction to the max margin solution. So the max margin solution is given here. It is the solution with the minimal L2 norm, such that it classifies all the training examples correctly with margin of at least 1. Okay, so the sign of the output for each example size should correspond to yi, and the output should be at least 1. And this is the max margin problem, and specifically for the case shown in this figure, it means that we will converge to the left linear predictor. Yeah.
This problem seems so basic. Has it not been asked before 2018? It seems a bit surprising. No, something.
No.
It's kind of the wrong way to find the solution, right? I mean, there is a very natural algorithm that finds exactly this solution. It's called support vector machines, right? But you're asking now about a different algorithm that somewhat surprisingly converges to the same algorithm, to the same solution side.
So instead of asking what is it doing on the algorithm to work well, we want to do it in the opposite way. We want to understand why it works well, although we don't see a reason for why it should. Yeah.
And this does not depend on the initial condition, initial point?
No, it does not depend on the okay, so this theorem gives a nice characterization of the implicit bias because it says that from the large set of possible solutions, we only converge to a very specific solution, only to the max margin solution. So the training algorithm is biased towards margin maximization, and it is called implicit bias because this bias is implicit in the training algorithm. We did not state explicitly that we want to maximize the margin. We just use the standard algorithm, and the standard algorithm happens to prefer max margin solutions.
What is the indirection in brackets there, in parentheses?
Yeah, I mean, asymptotically, the norm of W will go to infinity, but we care about the direction of the
Okay.
Okay, now the question is what happens in nonlinear neural networks. With this theorem by UNV and Jean Bergasse, they considered a large class of neural network. I will not define formally the assumption about these networks. I will just say that this assumption holds in all of the networks that we will discuss in this talk. And they proved that gradient flow converges to a KKT point to the max margin point. So when we consider nonlinear networks, the max margin problem is defined in an analogous way to the definition in the case of linear predictors. But now we want to minimize the norm of the parameters. We'll review the parameters as a vector. And we want to do it while classifying all the examples correctly with margin of at least 1. Okay, so the sum of the output should correspond to yi, and the absolute value should be at least 1 for each training example. So this is the max margin problem. And in this case, for nonlinear networks, the theorem said that we converge to a KKT point of this problem. Now, what is a KKT point? KKT point is a stationary point of this max margin problem, and formally it is defined as a point that satisfies some set of equations which are called the KKT conditions. And for this talk, we will not really care about the details of these equations, so we don't have to read these equations. The only thing that we need to understand is that the theorem says that from the large set of possible solutions that fit the training data, we only converge to very specific solutions, and we only converge to solutions that satisfy these equations. Now, it is worth mentioning that these KKT conditions are necessary but not sufficient for optimality. So it is possible that we converge to a KKT point, which is not an actual max margin solution. The theorem does not guarantee that we converge to the global optimum of the max margin problem. It only guarantees that we converge to this stationary, this KKT point. Intuitively, we can think about the theorem as implying that there is some kind of tendency towards margin maximization because we converge to this stationary point of the max margin problem, but it is not guaranteed. And it is analogous to the case where we run gradient descent on some function and we reach a point where the gradient is 0. But this point is not necessarily a global minimum of the function. So also here, this KKT point is not necessarily a global optimum. Okay, so just to emphasize again, in case you missed some of the details, the only thing that we really need to understand about this theorem is that it says that from the large set of possible networks that fit the training data, we only converge to very specific solutions, and these specific solutions satisfy these equations, which are called the KKT conditions. And so these KKT conditions give a given characterization of the implicit bias in this case of nonlinear networks.
So what is it about gradient flow? It kind of respects the L2 data, the parameters.
You're asking why this is the case?
I mean, I wouldn't expect necessarily the L2 norm from gradient flow. So is it something about?
Well, in the case of linear predictors, would you expect L2 norm?
I mean, I wouldn't know what to expect, minimizing something, but
yeah. So I mean, the intuition here is more complicated perhaps, but for linear predictors, well, basically, since we consider the logistic loss, then in each iteration, in some sense, the important point, the point that affects the gradient, is the point with the smallest margin. So, and so because this logistic loss function has an exponential tail, it causes the phenomenon that in each iteration, the important points are dealing with the smallest margin. And so asymptotically, we always like balance the margin between the points. So this is perhaps the intuition, but yeah, of course, it's not true.
Another question. You say that the problem here also minimizes the size of the parameters.
Yeah.
This is something maybe obviously when you define the logistic loss, do you also try to minimize the size of the weights of the network?
Yeah, so the parameters are the collection of all weights, weight vectors, and path vectors.
And this is part of the loss function for the.
No, it's not. No, the loss function is just minimizing the logistic loss over the training data set. So we don't have an explicit generalization, but implicitly, it turns out that we minimize this. So we want to understand some implications of implicit bias, and we'll start by discussing implications on probability generalization, and we call it understanding generalization is the main motivation for the study of implicit bias, and indeed we'll show that implicit bias can lead to good generalization in some situations. And then we'll show that the implicit bias also has some more negative implications. Specifically, we'll show that it can lead to better adversarial robustness and to some privacy issues. So we'll start with the first two implications. Empirically, we already mentioned that overparameterized networks in many cases tend to generalize well, but also to be vulnerable to adversarial examples. So these observations, these empirical observations, might suggest that the implicit bias is a double-edged sword, in the sense that it might be good for generalization, but bad for adversarial robustness. And then the main questions are whether we can actually prove that this is the case, or whether we can understand in what situations the implicit bias indeed leads to good generalization, but bad adversarial robustness. And I think that these questions are important because by understanding when overparameterized networks tend to generalize well, but to be non-robust, we might be able to improve generalization or to improve robustness. And in order to better understand these questions, we will now consider a relatively simple setting in which we have a two-layer network of depth 2, and where the data consists of clusters. And of course, the motivation to study a relatively simple setting is that in order to understand these more general questions, it might be helpful to start with a setting that we can actually analyze analytically. So the setting is as follows. We consider a two-layer network, such as in this figure, and this network computes function of the form which is shown here. And we will assume that the data consists of k clusters. So the data distribution is a mixture of k Gaussians, and it means that in order to choose a random example, we first choose an index j between 1 and k. This is the index of the cluster. And then we choose x from the Gaussian distribution with some mean mu j. And then the label corresponds to the cluster. So for each cluster, we have some label yj, which is the label given to all examples from the cluster. So it's a very standard setting of k clusters. And we'll assume that the size of the cluster mean is square of d, where d is the input dimension. So it corresponds to the case where each coordinate in the input is a side of one. And also we'll assume that the number of clusters is not too large and the correlations between clusters are not too large. And instead of specifying the technical assumption about having not too many clusters and not too large correlations, I will just give one typical example and we can just think about this example when we discuss the results. Yeah.
What are the Y's here?
The label.
So they are plus minus one? Or they are-
Yeah.
So they're not. So they say y equals
So
y.
each cluster is fully contained.
What is y?
For an example.
Why are the labels?
Yeah.
Why are the running labels?
How do you choose the ones?
So each cluster has some yj, which is the label given to all examples from the cluster.
Either minus one, either or plus one.
So every cluster has a label of +1 or -1 and okay.
Yeah, so let's think about this typical example where we have at most square-root clusters, and we think about the cluster means as random vectors. So basically, we choose each cluster mean to be a random vector on the sphere of radius square-root. And also suppose that the radius of each cluster is roughly square-root. So the radius of each cluster roughly equal to the size of the cluster. Yeah? So in this case, our assumptions fall without probability, and so when we discuss the results, we can just think about this case where we have at most square-root random clusters. Okay. Now we want to understand whether it's about leads to good generalization and whether it leads to good adversarial robustness or not. And we start with generalization. We show the following theorem. Suppose that the number of training examples is larger than the number of clusters up to some log factor. Then we show that if gradient flow reaches some sufficiently small training loss after some finite time, then it converges to a network that generalizes. So basically, theorem says that if gradient flow does not get stuck in some local minimum of the training loss, if we manage to reach small training loss, then we converge to a network that generalizes well. And note that the theorem is independent of the network width. So even if the network is very, very wide, and with wide networks, we can essentially approximate any function. We can approximate any continuous function. Still, gradient flow will only converge to very specific functions, and the functions generalize well in our cluster setting. Okay, so even if the network is highly overparameterized, the implicit bias prevents harmful overfitting. And the way to prove it is by showing that every KKT point of the max margin problem in our setting, in our cluster setting, every KKT point generalizes well. And since there is implicit bias towards KKT points, we can only converge to solutions that generalize. Okay, so this result shows that the implicit bias in this case is good for generalization, and now we also want to understand adversarial robustness.
So, the variance of the clusters, what do you assume
About
the variance?
yeah, so the radius of each cluster is roughly square-root in our which is also the size of the cluster.
So in this model, basically you get that the data is linearly separable.
Yeah, so in this case, the data can be linearly separable, but of course, when you train an counter network, you will not converge to the linear classifier, you will converge to, I mean, you can converge to any function essentially, and the question is to which function you will converge. So in this case, we will not converge to the linear class. Yeah.
I didn't understand, how do you conclude that implicit bias prevents harmful overfitting?
Well, because the implicit bias says that we can only converge to KKT points, and we prove that every KKT point generalizes. So it means that we can only converge to networks which generalize.
So I thought we had two criteria, one is generalizes well, and second, it's not it's not vulnerable to
Right.
adversarial.
Yeah, so here we talked about the first one, and now we're talking about the second.
Okay.
So getting back to the radius, you said it's square root d. What's the distance between centroids? Is that
It's
where
also roughly square-root. All square-root. Set of square-root. Yeah. Okay, so now in order to understand adversarial robustness, we can first think about the simpler case of linear predictors, And in linear predictors, we said that the implicit path towards margin optimization. And margin optimization for linear predictors is good for adversarial robustness, because maximizing the margin is equivalent to maximizing the distance between the decision boundary and the data points. And this is good for adversarial robustness. And then the question is whether this intuition also holds for nonlinear neural networks. And we will show that the answer is essentially no. We'll show that for nonlinear networks, the implicit path towards margin optimization can be highly non-optimal for adversarial robustness. And in order to show it, we need to show two things. First, we need to show that in our setting there exist networks which classify the data correctly and are also robust. And then we need to show that although such good networks exist, we will not converge to them because the implicit path will prevent us from converging to these good networks. So let's start with the first part. We show that there exists a two-layer network such that if we choose a random test example, then with our probability it is classified correctly by this network. And flipping the sum of the output requires a perturbation of size at least omega square root d, where d is the input dimension. And as I said, the distance between each clusters is roughly square root d, so this is essentially optimal in terms of adversarial robustness. But now we'll show that although such a good network exists, we will not converge to it. We know that for every KKT point of the max margin problem, namely every network that we can actually converge to. If we choose a test example, then with our probability, we can flip the sum of the output with a perturbation of size of square root d over k. So if the number k of clusters is larger than a constant, then the robustness is non-optimal. For example, let's recall the case that we mentioned before, in which we have square root d random clusters. And in this case, we can plug in k equals square root d, and we get that the size of the perturbation is roughly d to the quarter, so, which is of course much smaller than square root d. So in this case, where we have square root d random clusters, the robustness of the solutions that we can converge to is highly non-optimal. Okay, so yeah.
How do you measure the size of the perturbation?
L2 distance between the input and. So to conclude this discussion about the cluster of the data, we started by saying that empirically, it seems that in many cases, trained networks tend to generalize well, but to be non-robust. And then we proved that indeed the implicit path leads to good generalization and to better adversarial robustness in this case of cluster data. Yeah.
Does your result about two-layer network about linear functions, does it like the positive result about the linear one generalize beyond the two-layer network?
You mean this part?
Yes.
No. So if you have a linear predictor, you cannot have a robust classifier for in this setup. You must have at least two layers in order for a robust classifier to exist in this case.
I mean more than two layers.
More, yeah. So of course, yeah. So for more than two layers, of course, there exists robust classifiers, but then the negative results, perhaps it holds and perhaps not. We just proved it for the two layers. Okay, now we'll discuss the third implication about privacy. We'll show that the implicit path can lead to some privacy issues. And the main question that we consider is whether we can reconstruct training data from the parameters of a trained neural network. So we're given a trained network, and we want to understand whether, given this network, we can find some examples that were used for training the network. And perhaps surprisingly, we'll show that the answer is yes, that at least in some cases, we can reconstruct training data from a trained network. And we'll show that we can do it by using the theoretical results about the implicit path towards the KKT points of the max margin problem. And of course, the ability to reconstruct training data might have negative implications on privacy because the training data might be sensitive, for example, medical data. And hopefully, by understanding in what situations neural networks leak information about the training data, we might be able to improve privacy. So, before I start how the method works, let's show some results. So here we train the network with a dataset of size 500 of images from C410, which is standard dataset for image classification. And the labels are animals versus vehicles, so it's a binary classification setting. And we trained a network with 3 fully connected layers. And then given this trained network, we tried to construct the training examples. And here in rows number 1, 3, and 5, we see the constructed images. And in the rows below them, we see the original images from CIFAR10, which corresponds to the constructions. And we can see that in this case, we get many high quality constructions. Okay. Now, of course, the question is how does it work? And we call these equations of the KKT conditions. And we said that the implicit bias implies that when we train the network, we converge, we're given some training data set, and the training algorithm converges to some parameter theta that satisfy these equations. Now, in order to construct training examples, we're essentially trying to do the reverse process. Because we do not know the training data set, but we know the parameter theta, and we know that these equations are satisfied. So we're trying to find some data set that satisfies these equations with respect to the given trained parameter theta. So this is the main idea of the method, and more specifically, we rely mostly on equation number 1, which is called the stationarity condition. And in order to try to solve it, in order to try to find a data set that satisfies it, we're minimizing this objective. And note that this objective gets a value of 0 exactly when we have a solution for this equation. So we're trying to find a data set that satisfies equation 1 by minimizing this objective. Yeah.
Is this method directed at the entire data set at once, or can you just try to have specific images?
We try to find every single one.
So is it like if you have the entire CIFAR database itself, if you go to ImageNet, there are very big data sets.
Right. So we also extended the results also to multiclass classification and to construction from convolutional neural networks. So the method also applies not just to fully connected networks, but also, for example, for convolutional neural networks. Now, as you asked, indeed, in the example that I showed, the size of the data set is relatively small. It's 500. And in some additional experiments that we conducted, we were also able to construct images from a data set of size up to 5,000. But even 5,000 is very small compared to what is commonly used in practice. And so it is a very interesting question of whether reconstruction is possible also with larger data sets. And more generally, whether it is possible to construct training data in settings which are more realistic, settings that are actually used in practice. So I think that it is a very interesting question. And another interesting future direction is to try to understand implicit bias, whether there is implicit bias towards good generalization, also in other architectures and distributions. For example, in attention mechanisms, in transformers, which are very common in practice today, the implicit bias is not well understood. And it is certainly not well understood when the implicit bias leads to good generalization. So I think that trying to understand this question for transformers is a very interesting question. So to conclude this discussion about the implicit bias, we said that the implicit bias seems to be key for the static generalization, and we showed that in some cases it probably leads to good generalization. And then we also showed that the implicit bias is useful also for understanding other aspects of deep learning, such as adversarial robustness and privacy. Now, now I will turn to discuss benign overfitting. We say that we have benign overfitting when the learned predictor, on the one hand, interpolates noisy training data, namely it perfectly fits noisy data, but still it generalizes well on the test data. Okay, so here when we consider benign overfitting, we're talking about noisy training data, which means that we have label noise, that the labels in our training data are noisy. And this notion of benign overfitting started from some empirical evidence by Zhang et al., in which they trained over-parameterized networks on standard tasks with noisy data, and the network interpolated the training data, but still generalized quite well. And this observation was very surprising because traditional understanding in machine learning theory says that it is not a good idea to perfectly fit noisy data. If we interpolate noisy training data, then we are essentially overfitting the noise, and in such cases, we should not expect good generalization. But still, in practice, it seems that it works quite well. And starting from this empirical work, there have been a huge number of theoretical works that try to understand in what situations this phenomenon occurs. And indeed, understanding how neural networks can generalize well, even when we interpolate noisy data, seems like a very fundamental question for understanding generalization. And I will try to illustrate this notion of benign overfitting using this simple illustration. So suppose that we have data which roughly corresponds to this linear predictor, but we have some label noise. So the optimal predictor is this linear predictor, but the data is noisy. And if we train an overparameterized model on this data set, one possible situation would be harmful overfitting, in which we interpolate the data, the training data, but we do not generalize well. We'll test examples. Another situation, which is perhaps possible, is benign overfitting, in which we interpolate the noisy data, but still we generalize like the optimal predictor. So if we choose a random test example, then with high probability, it performs like the optimal predictor. And so this is the definition of benign overfitting, where we interpolate noisy data, but we still have optimal generalization performance. And it is called benign overfitting because we're overfitting the noise, but we're doing it in a benign way, in a way that does not hurt test performance. And of course, this is not an experiment, it is just an illustration of this notion. For this specific data set, if we train a network, we will not get benign overfitting. Now, as I mentioned, in recent years, there have been a huge number of theoretical works that try to understand this phenomenon, and most of these works focus on linear models, namely either linear regression or linear classification. And so in these works on linear models, they try to understand under what conditions on the data distribution we get benign overfitting. And our understanding of benign overfitting for nonlinear networks is much more limited. There are these two prior works in which they consider benign overfitting in fully connected two-layer networks, and they consider a setting with two opposite clusters, one with positive labels and one with negative labels. And we have some label flipping noise, which means that we flip each label with some positive probability. And they showed that under some conditions on the registers of the clusters, we get benign overfitting in this case. And an important thing to note about all of the existing results on benign overfitting, both the results on linear models and the results on nonlinear models, is that in all of these existing results, the input dimension is larger than the number of training data. So all of these results consider high dimensional data. And of course, this high dimensionality is a strong assumption because practical settings are often not high dimensional. So this is a limitation of all of the existing results on benign overfitting. And given this picture, I want to discuss two main questions. The first question is whether we can show benign overfitting in fully connected neural networks, also in such settings which are more general than this specific case of two opposite clusters. And the second question is whether benign overfitting is possible also in low dimensional settings, in settings where the input dimension is smaller than the number of examples. So let's start with the first question. In a recent work, we showed benign overfitting in two-layer leaky web networks in two main settings. The first setting considers K clusters, and we showed that under some assumptions on the register of the clusters and the correlations between cluster means, we get benign overfitting. And the second setting considers sub-Gaussian data where each coordinate in the input is independent sub-Gaussian. And we showed that under some conditions of the covariance matrix, we get benign overfitting. And these two settings are more general than this previous setting of the two opposite clusters, in the sense that they include the previous setting in a special case. So these conditions are more general than the previous results that I mentioned. Also, in another recent work, we proved benign overfitting in two-layer Weyl networks. in a setting where the data is an XOR pattern, which roughly looks like this figure, where we have two opposite positive clusters and two opposite negative clusters, and we have some level fitting noise, and we show that under some conditions on the radiuses of the clusters, we get benign overfitting. And this setting where the data is an XOR pattern, and also a variance of this setting like sparse parities, attracted interest in visitors, mostly because these are simple cases where every linear predictor has trivial test performance. So these are simple cases for distributions which are truly nonlinear in a sense. Okay, so
Yeah, in the first result, the leaky part. What's the dependence on the slope there? What happens if you take it to 0?
yeah, so right, so if the slope, we think about the slope as a constant. If you take it to 0, then the result does not hold. It doesn't mean that we don't have benign overfitting. It just means that the proof will go. So from these results, we can see that benign overfitting can occur in fully connected neural networks in various settings, and not just in this specific case of two opposite cluster. But it is worth mentioning that also the new results consider high dimensional data. So also in these new results, the input dimension is larger than the number of training examples. And so this second question about whether benign overfitting is possible in low dimensional settings is still an open question. And I think that an interesting direction for future research is to understand how interpolating neural networks generalize well in low dimensional settings. Namely, how neural networks can generalize well even when we interpolate noisy data in settings where the input dimension is smaller than the number of examples. And since in practice this is often the case, practical settings are often low dimensional in this sense, then I think that it is an important future direction. And I will elaborate a bit more about this future direction. So there is some recent empirical results by Marina et al., in which they trained over-parameterized networks on noisy data on standard tasks in cases where the data is low dimensional. And it seems in the experiments that we don't have benign overfitting, but we also don't have catastrophic overfitting. They called this intermediate regime tempered overfitting. And tempered overfitting means that if we think about large data sets, if we think about the limit where the number of samples goes to infinity, then the predictor does not approach the base optimal predictor. So we don't have optimal generalization performance, and therefore in this sense, we don't have benign overfitting. But still, the trained predictor is much better than a random guess. The test performance is not trivial. It's much better than a random guess. For example, if we have a binary classification setting and we flip each label with a probability t, then in this case, the test error cannot be smaller than p because we have this label noise in our data distribution. So the test error cannot be smaller than p. But if we train a network which interpolates the training data, then the training error is 0. So there is a gap of at least p between the training error and the test error. So in this case, let's suppose that the base optimal performance is test error of p, and suppose that we converge to a network where the test performance are 2p. So in this case, we don't have benign overfitting because the test performance is 2p and not p, but still it is much better than a random guess. So in this case, we can say that we have tempered overfitting. Okay. Now, if we combine these empirical results with the fact that all theoretical results require high dimensionality, then I think that in order to understand how neural networks generalize well, even when we interpolate noisy data, it might be important to understand this regime of tempered overfitting in low dimensional settings. Okay, so to understand the test performance of interpolated neural networks in settings where the input dimension is smaller than the number of samples. And as the first step in this direction, we already considered the very low dimensional case where d equals 1, where the network is univariate, such as in this figure. And in recent work, we characterized tempered versus catastrophic overfitting for univariate networks in a regression setting. Also, there is another recent work by researchers from the Weizmann Institute in which they studied the same question in a classification setting, and they showed that they proved the tempered overfitting for univariate networks for classification. And so even this univariate case, which seems very simple, is highly non-trivial to analyze. However, I think that for this univariate case, we already have a reasonably good understanding of the overfitting behavior. But even for d equals 2, we already don't understand this question. And I think that an interesting next step would be to try to understand tempered overfitting or overfitting behavior in low-dimensional settings where the input dimension is larger than 1. Okay, so in the first part of this talk, we considered implicit bias. And then in the second part, we discussed benign overfitting. And these two concepts seem to be crucial for understanding generalization in deep learning. And indeed, this question of how neural networks generalize well, or in what situations neural networks generalize well, seems like a very fundamental question in machine learning theory. But despite much efforts, we don't have a good understanding of this question. And so I think that understanding this question about generalization is a very interesting and important long-term research direction, and we should keep exploring the different aspects of this question. And I hope that new theoretical insights on generalization will also lead to improved performance in practical systems or to achieving good performance with less resources or less training data. Okay, thank you.